Hello, grade 12s. Today we're going to be talking about probability of events with and situations, which means we are talking about not only just one event happening, but two events taking place, and we want both of those events to occur. So when we talk about something like that, where we have two or more, perhaps, different events taking place, and we want both of them to occur, we kind of arise in two different situations. Those events can be independent events. Independent events are events whose outcomes are not affected by each other. So, for example, the Bombers winning the Grey Cup and the grade 9 SMA basketball team winning their next game, right? Each of those has an associated probability with each other, but if the Bombers win or the Bombers lose, it doesn't really impact how the grade 9 basketball team is going to do. So if I want to talk about both of those teams winning, the Bombers winning and the grade 9s winning, in and situations, just as we've mentioned before, we multiply. So you'll notice we have multiplication in all of these situations. We see similar notation in our and situations to what we would have talked about in Unit 4. And in the and situations, we talk about the intersection of two events taking place. So that's the overlap between them, but specifically overlapping in terms of whatever outcome we're interested in. So both event A takes place, so the Bombers win, and event B takes place, so SMA grade 9 basketball wins. How we do that is we simply take the probability of one and multiply it by the probability of the other. So a really simple example to get us going with here is to talk about the probability of flipping two coins and getting a heads on each. Now, when we're defining our events, we'll want to define each event separately. So I'm going to define the first event as A, just so it can match the formula there. So my first event will be getting a head on my first coin. And my second event, I'll call it B, will be getting a head on that second coin. Now, if I flip one coin and I get a head, it doesn't impact how that second flip is going to occur. I still have an equally high chance of getting a head or a tail. Nothing happens, so these are independent, which means if I want to find the probability of getting a head on the first one and a head on the second one, I simply multiply those probabilities together. The probability of A, well, I have a 1 out of 2 possible chances getting a head. The probability of B, same idea. I have 1 out of 2 chances to get a head on that second coin, and I simply multiply them. 1 half times 1/2 gives me 1/4. If you plug this into your calculator and get 0.25, that works too. Just quick reminder though, multiplying fractions, we go numerator by numerator, denominator by denominator. Okay, that's independent events. We also have dependent events. And dependent events are two or more events whose outcomes are affected by each other. So, example can be like, let's say, I am pulling out socks from my drawer. They're unmatched. They're just completely loose in there. And I want to figure out the probability of pulling out a white sock first and then a white sock second, because I want to aim for a match here. But of course, maybe it's dark, it's the middle of the night, don't have the lights on, and for whatever reason, I just woke up, my feet are cold, and want to put on socks. So I'm just grabbing them at random. I'm not really looking. Now, of course, if I have a whole bunch of different colored socks in there, my probability of picking out that first sock is simply however many white ones I have available, divided by my total. But the probability of pulling out that second white sock, well, because I'm not putting my first one back, what would be the point of pulling it out if I'm just going to put it right back in the drawer? Well, now I have one less white sock to choose from if I had pulled out a white sock first, and one less sock in the total to choose from, because, again, I pulled out a single sock first. So pulling out that second sock, that probability is going to be impacted by the result of my first pull. So that's an example of dependent events, where what I do in my second event will be impacted by what I do in my first event. So you'll notice some similarities here. I'm still talking about an and situation, so I still have that intersection. Because of that and situation, I still have multiplication. My first event probability isn't impacted by anything because nothing has happened yet. But my second event probability, I have a little bit of a different notation. So I still have the P bracket. That still means the probability of. But on the inside here, we have the probability of event B happening. So whatever that event is, pulling out a second white sock perchance. Given that, or such that straight vertical line, that's what it refers to, given that event A has taken place. So that's how we read it. And we'll talk about more of that in just a moment. But let's just quickly talk about the idea of those dependent events. So if I'm talking about a situation here, I have a bag of 10 chocolate bars inside, 3 are Kit Kats and 7 are Aeros. What's the probability of pulling out 2 Kit Kats without replacement? One of the key things in this question that I want to point out is the fact that it says without replacement here, which means I'm not putting back the Kit Kat after I pull it out, or that Aero bar after I pull it out the first time, right? I'm keeping it out, which kind of makes sense. What's the point of putting it back in there? With that being said, without replacement, anytime I have no replacement and I'm pulling out of like a group, that's going to be a dependent set of events. Where if I have with replacement, well, my probability isn't impacted because I have like a clean slate every single time. So kind of a hint there in terms of identifying the difference between independent and dependent events. All right, moving forward, let's figure that out. So my first event that I'm interested in, because I want to pull out 2 Kit Kats, is pulling out a first Kit Kat. And my second event would be pulling out a second Kit Kat. And I could see that the probability of both occurring is going to be the probability of the first one occurring. We'll have 3 Kit Kats out of 10 possible chocolate bars, so 3/10 is that probability. It's an and situation, so I multiply. And the second one says the probability of B, given that A has already taken place. So what's the probability of pulling out a Kit Kat if I've already pulled out that first Kit Kat? Well, that means there's only 2 Kit Kats left to choose from, and there's only 9 chocolate bars left in that bag. Again, I could do that multiplication, so numerator times numerator, denominator times denominator, and I can math frac that. I get that reduction to be 1/15. All right, so those are kind of our 2 introductory examples here to those dependent and independent events. Let's dive deeper into conditional probability. So conditional probability, again, is the probability of an event occurring given that we know another event has already taken place. So conditional means we already know something has happened, and because something has happened, that's going to impact our probability, which makes it conditional. This conditional probability only occurs when we have dependent events, and we still treat it the same in terms of the multiplication in our and situations, but we have to kind of use this conditional version of it. Just to kind of point out what the notation pieces mean. This P and then the brackets, that still implies the probability of. Move this arrow here. Okay. This B coming first is talking about that second event. So the second event taking place. This straight vertical line means given that. And this A that's my first event. So that's the first event, but because it comes after that vertical line, that implies the first event has already occurred. It's already happened. It's already taken place. So that's kind of how we look at that. That's the probability of my second event taking place, given that the first event has already occurred. Okay, so depending on what we have in our examples, we could give it some context, like the probability of pulling out a second Kit Kat, given that we've already pulled out the first Kit Kat. We could give it some context in our situations, but that's kind of the general interpretation of that probability. All right, we're going to jump right in, and we're going to actually stop using letters A and B here because oftentimes we call events based on what makes sense contextually. But we used A and B just to start practicing and matching those, the general notation. So jumping right in, a computer manufacturer knows that for every 100 computer chips made, 3 of them will be defective. Jocelyn will draw 2 chips at random from a box of 100 chips. Show your work using proper notation to determine the probability that Jocelyn will draw 2 defective chips. So Jocelyn's reaching in, grabbing 2 chips at random, not looking. And we want to know what the probability of the first one being defective and the second one being defective. Okay, these events are dependent because there's nothing that says that Jocelyn's putting the chips back into the bucket or into the box after she's done. But also, it doesn't make sense that she would, right? Unless we're just trying to see what we get and putting it back. Maybe like one of those carnival duck games or something like that. But realistically, there's no information telling us that she would put those things back. So we're taking a look dependent. I'm going to name it my sets F and S for first and second. So the F will be the first chip pulled is defective. And I'm going to use S to say the second chip pulled is defective. And I want to know the probability that both are going to be defective. So I want to know the probability of the first and the second chip that I pull or Jocelyn pulls will be defective. Since I know that these events are dependent, I know the probability of the first won't change because nothing's happened if you're doing it for the first time already. So P of F will be the regular clean slate kind of situation. But that second event's probability will be impacted because I know that first event will already have had occurred. Now, to find the probability of the first chip being defective, well, we know that 3 out of 100 chips are defective, and she's pulling it out of a box of 100. So we have a 3 in 100 chance of pulling that first defective chip. To pull a second defective chip, that's assuming that she's pulled out a first defective chip, which means if there was 3 to begin with, she's already pulled out 1, there's only 2 left. And because she's pulled out 1 from that total sum of 100 chips, there's only 99 totals that she could technically pull out. I multiply because we have that and situation giving us 6 over 9,900. I'm not 100% sure if your calculator will reduce this or not for you. If it does, you end up getting 1 over 1,650. If it doesn't, you could reduce manually as well. I acknowledge that both the numerator and the denominator are divisible by 6 because the denominator is obviously even, it ends in a 0, but also divisible by 3 because its digits sum to something that is divisible by 3. And if we're divisible by 2 and 3, we're divisible by 6. I could also see if it works, and if it does, life is good. But it reduces all the way down here. All right, we're going to take a look at another set of examples. In this case, we have Erin. She's drawing cards from a well-shuffled standard deck of 52 playing cards, and she draws another from the deck without replacement, which again is a nice little hint here that I have dependent events. So without replacing that first card. We want to find the probability that both cards are jacks. So I'm going to stick with F and S here because if I use J and J, that's too confusing. So first card is a jack. Second card is a jack. And I want to find the probability that both are jacks. So the probability of the first and the second being jacks. I know these are dependent because there are no replacements. So I have the probability of the first. I know it's an and situation, so I multiply it with the probability of the second. Since that probability is impacted by the first already having taken place, it's conditional. And I can figure out those numbers. There are 4 jacks in a deck of cards. There are 52 cards in a deck of cards, so I have 4 over 52. If I had pulled out one already, there's only 3 remaining jacks, and now there's only 51 remaining cards. I could perform that multiplication, and I get 12 over 2652, which reduces to 1 over 221. At this point in time, I really do think that the next 3 examples, B, C, and D, you would be able to do on your own. If you want to give it a go, please pause the video, try it, and then come on back. But otherwise, I'm going to start tackling the next ones right away. So same idea. I want to figure out the probability that both cards now, but they're face cards. So I'm going to probably use F and S again. F for first card is a face card. And S for second card is a face card. Really doesn't matter what letters you use, as long as it's obvious to you and it's defined which one's which. If I want to know the probability of the first and second being faces, well, I know the first probability is not impacted because nothing's happened, but my second will be because I'm not replacing anything here. Please note that the order of this conditional probability really matters. Realistically, if these were independent, I would just have probability of the first times the probability of the second. The difference being, since my second depends on my first, I need to have that second come first and tell me what it's dependent on. Okay. Taking a look at that face card. So face cards are cards with a jack, queen, or king on it. There's a jack, queen, of king out of all 4 of those available suits, which means there are 12 face cards in a deck out of 52. And my next one, if I pull out a face card first, that means there's only 11 left, with a total of only 51 cards remaining, leaving me with 132 over 2652, which does reduce to 11 over 221. Okay, the next one, determine the probability the first card is a 9 and the second card is a 10. I'm going to use some different letters here just to spice things up. I'm going to use N, that my first card is a 9. And I'm going to use T for my second card is a 10. And I want to know the probability of the first one being 9 and the second one being 10. I know this is conditional because I'm not replacing the card in that deck. So the 9 was my first card, so the probability of N, times, because it's an and situation, the probability of getting a 10, given that I've already pulled out a 9. For my first probability, it is clean slate, nothing's already happened. There are 4 9s in my deck out of the 52. Now for my second probability here, I know that I haven't actually pulled out a 10 already, so all 4 10s are remaining. It's just now that one card out of my total deck is missing, one of the 9s, so I only have 51 options going on. Now this example is very important because in all the previous ones, we noticed that both the numerator and denominator decreased by 1 as we kind of went on. And that only happened because I'm looking for the same thing twice. But if I'm looking for different things, I won't notice that numerator decreases because I'm looking for 2 separate things. That's a separate piles to pull from or separate values to kind of consider. But my denominator decreases because my total has now differed. When I multiply, I get 16 over 2652, which reduces to 4 over 663. Now, how would I have to change this question in order for these events to be independent? Well, we pointed out the reason that they were dependent is because we did not put that first card back after we pulled it. So, if you put the card back after you draw the first one and before you draw the second, these will be independent events. So let's write that. If you put the first card back in the deck before drawing the second, the events would be independent. Essentially, by putting that card back after drawing it and putting it back into the deck, you've essentially restarted everything. You've got back to that clean slate where nothing has seemingly already taken place. All right, let's jump into a couple of examples that maybe are a little bit less obvious in terms of like counting or finding that probability. How could we read that information from a question? And would we ever want to find something that's not that intersection? Maybe we want to find the conditional probability. So that's what we're going to take a look at here. We're going to look at some cases where we're not necessarily always looking for the intersection. We're looking for another piece. But if we have the other two remaining pieces of the 3 in my equation, I can go ahead and solve for that unknown. So let's take a look at our first question and try and identify what information we have. So the probability that it is Friday and that a student is absent is 0.03. Since there are 5 school days in a week, the probability that any school day is Friday is 1/5 or 0.2. What is the probability that a student is absent given that today is Friday? So there's 2 probabilities we know. And those are the probability that it is Friday and a student is absent. So I know that and piece will likely be talking about that 0.03 is talking about my intersection between the sets because of the word and. I also know that the probability that is Friday is 0.2. Right? That only talks about it being Friday, does nothing to talk about in terms of absence. So that's going to be my individual probability. And I'm looking for the probability that a student is absent given that today is Friday. So this is going to be my conditional probability I'm looking for. And the words given that are a really big hint that that's what I'm looking for here. So I need to set up and define some events because I can't just use A and B. I don't know what A is. I don't know what B is. But looking at both my yellow and my pink things that I've highlighted here, my first probability talked about Friday and absent. And the pink one talks about absent given Friday. So I know that my 2 events that I'm considering here, one is F being it is Friday. And maybe A, that a student is absent. Now, the reason why this is very helpful is I can kind of take a look and say, okay, well, let's identify what probabilities I have now that I know my letters. So this one here would be the probability of Friday and absent. This purple one here is the probability of just Friday. And this one here is the probability that I'm absent given that today is Friday. And because I have all of those pieces, I can set them up accordingly in the same order as my formula here. So I know that the intersection is equal to the probability of the first one. I know P of F is the first one because it's alone, clean slate, nothing's already happened. And my second event would be the conditional one. I know it's an and situation, so I know I need to multiply. And here I can input those numbers. So I know that both the intersection 0.03, I know Friday is 0.2, and I don't know the last one. That's what I'm looking for, so I'm going to leave it as is. We're going to do some reverse algebra here, some reverse BEDMAS, where I undo the multiplication by 0.2 by dividing 0.2 on both sides. And we end up, when we do that division, getting 0.15 is equal to that conditional probability. Oops, battery's low. So it's equal to that conditional probability. All right. Things to kind of just keep in mind. Remember that probabilities as decimals can only be between 0 and 1. So if you get a number that is greater than 1 for whatever reason, please acknowledge that that is some sort of mistake. It is not possible for that to happen. So if for whatever reason you switched up the 0.2 and the 0.03, and when you do that division, you would have gotten a number greater than 1. Because I know probabilities can't take on a value greater than 1 if they're in decimal or fraction form, I know that that's not a possible answer, and it would be a good kind of indicator for me that I need to go back and check my work. Okay, let's jump to the second one. So the probability that Sue will go to Mexico in the winter and France in the summer is 0.40. That word "and" there probably again indicates that I'm talking about the intersection. The probability that she'll go to Mexico in the winter is 0.6. I notice that it's only one thing that's the probability, so that's likely my first event. And I want to find the probability she will go to France this summer now that we know she has just returned from her winter vacation in Mexico. Now this here is a conditional probability, the last one that I'm looking for. Even though I don't use the words "given that," I know that conditional probability is taking place when my probability has changed, knowing that something has taken place. And I know that Sue has just come back from her vacation in Mexico, so I know that has taken place. So even though the words "given that" or "such that" or "knowing that" aren't necessarily in there, I understand it's conditional because that's what conditional probability that's how it works, is that I know something's taken place, so I want to know the probability of the next thing now happening as well. I need to name some events. I've got Sue going to Mexico. I have her potentially going to France. So I'm going to use M and F. So Sue goes to Mexico for M. And F is Sue maybe going to France. And again, I can take a look at these probabilities. So the probability that Sue will go to Mexico in the winter and France in the summer, that's my intersection probability. So that's my Mexico and France. That's my both probability. So I'm just going to fill that in the line below. I know that the intersection of dependent events are going to be multiplying the probability of just the first event taking place, which is Mexico. And I know that one happened first because that's the one that's given to me as a single probability with no other information as. And I multiply that by the second event with the condition I already know the outcome of the first one. And that's what I'm looking for. I'm looking for the probability she'll go to France this summer now that we know she has just returned from her winter vacation in Mexico. I'm looking for that value. That is my unknown. This is where I'm at. Just like the previous one, reverse BEDMAS, undo that. Multiplication with division. I do that division in my calculator. I'm going to round my final answer to 2 decimal places. So I get 0.67. This, again, is a reasonable final answer because I know probabilities have to be between 0 and 1, and 0.67 falls within that. So this is my probability that she goes to France, knowing that she just got back from her Mexico trip. Okay, we have one more example. And this one more example is about Nathaniel and Rio. And they've just made up their own math game. How the game works is by having one player choose a number between 1 and 40. So that's all of the possible options. You can't choose 41. You can't choose 0. That's my total amount of numbers available to me. And then someone says a fact about that number. So Rio goes first and states that the number he chose is a multiple of 4. We want to determine the probability that the number is a multiple of 6 given Rio's statement. So remember, Rio's statement was that the number was a multiple of 4. So the fact that I said Rio's statement, I could really replace that saying given the number is a multiple of 4. Okay? The word given, kind of that hint, that key word we're looking for, or one of those key words that we're looking for that helps identify things as conditional probability. When I talk about conditional probability, I'm trying to find multiple of 6 given multiple of 4. So those two values are going to be my two events that are taking place. So I'm going to go ahead and I'm going to introduce those two sets. All right. So I'm going to say the first one would have been multiple of 4. That's the first part that came up. So I'm going to define F as number is a multiple of 4. And we're going to be doing some different things in this question because if you noticed, we didn't actually see any probabilities in the question. So we have to kind of deal and figure that out. And so just knowing that that's coming, I'm going to write my next set immediately next to it. So I'm going to call it S because the next one is the number is a multiple of 6. And realistically, what we're looking for, I'm going to leave a big gap in the middle here. But what we're looking for is the probability that it's a multiple of 6, given that we know it's a multiple of 4. So that conditional probability is what we're looking for. Now, the only way we've talked about finding conditional probability is if I'm part of this formula where I know the probability of both happening. I'm going to say the first one being a multiple of 4, or the number being a multiple of 4, and it being a multiple of 6. And I also know the probability of it just straight up being a multiple of 4, right? If I knew those other two pieces, I can use my algebra skills to figure out this probability, which I'm interested in. So let's talk about the other two probabilities. Let's start with this one here. The probability that a number that we chose is a multiple of 4. Well, I know I have 40 numbers to choose from, 1 through 40, right? That's how the game's played. I could only choose numbers from 1 through 40. I'm going to, instead of introducing that set as just a sentence here, I'm going to actually list all the multiples of 4 between 1 and 40. I've got 4, 8, 12, 16, 20, 24, 28, 32, 36, and 40. Now, if I were to count all of those numbers in that set, there's 10 of them, right? The number of elements in set F is 10. Now, just a quick reminder, the total number of numbers sounds ridiculous. The total number of numbers I could choose from in this game is 1 through 40. So I have a total of 40 different options. 10 of them are a multiple of 4. So if I want to find the probability, that's just 10 over 40, or 1/4. So what I'm going to do is I'm going to replace P of F with 1/4. Of course, I could choose to do this in decimal version. The reason that I don't choose to do this as a decimal is sometimes if my decimal goes on forever, it's not like an actual nice, like 2 decimal place decimal like a quarter is. I don't want to round too soon in my answer, so I like leaving things as fractions. It's a good kind of practice to follow. Okay, so we found one of those two things, so that's pretty cool. But I also, hey, that's not a highlighter. I also need to find this probability if I want to be able to calculate the conditional. So I want to find the probability that a number is both a multiple of 4 and a multiple of 6. So just because I've already written out all the multiples of 4, it would be helpful for me to visualize all the multiples of 6 between 1 and 40. So that's 6, 12, 18, 24, 30, and 36. Now, because I'm looking for the probability of them being both, I want to count how many of those numbers exist in both the multiple of 4 set and the multiple of 6 set. I'm going to highlight them to point them out, but I could just count as well. So 12 is in both, 24 is in both, 36 is in both, which means I have a total of 3 numbers that exist in both. Okay, well, my total number of options that exist does not change. There's still 40. 1 through 40 is all of the numbers in the game. So to find the probability of that, I simply take the total number of options and divide it by the total number of options that I can simply choose from, no conditions, no nothing. So that probability now is 3 over 40. And now I finally have enough information to solve for that conditional probability. So, same as before, I'm going to divide both sides by a quarter so that I can undo that multiplication. I might get my final answer as a decimal. I might get my final answer as a fraction. However I do it is equally okay. If I keep it in fractions, I'm going to get 3/10 is my probability of the number being a multiple of 6, given that I already know it's a multiple of 4. Or I might say 0.3, depending on how I kind of plug that into my calculator. But that's what I got. Now, that's really it for conditional probability. But I noticed in the previous years and past years, sometimes a few students would get confused between the probability of an intersection versus the probability of the conditional. So I just have here, and you could read it on your own, just a reminder of what those differences are. So the intersection is when I want both of them to happen at the same time. I want to know the probability of both events taking place. Whereas the conditional is I'm only looking for the probability of one. I just know information has already happened. I know that that first event has already taken place. Okay. Keywords for conditional probability. We've been using given that quite a bit, but such that is in there. If we know blank has already occurred, with the condition that blank has already occurred, and anything that's like a synonym for this. So having known that this has already taken place, knowing that this has already happened, with the information that blah is something that already took place, right? Anything that's like synonymous with that information is kind of the keys that you're looking for phrase-wise when we're talking about conditional. When we're talking about intersection, you're really just noticing that it's what's the probability of this and that happening. Or the probability of this and that happening is blah. In that intersection, we always see that word and. All right, that's the end of the section. There is some practice that follows. Otherwise, that is it for me. Have a great day and adios.